So I've told you already that alkynes are going to be one of the most useful carbon-carbon bond-forming tools you have in your toolbox, especially in the early going. But then comes the question of, okay, so once you've used the alkyne and once you've made something like this, what can you do with it after that? And if the answer is not much, then this synthetic pathway doesn't have much value. So we need to be able to functionalize it. We need to be able to convert this material into other useful things. So just to orient us, what I'm going to do is number these carbons. So this methyl arbitrarily is 1, that carbon's 2, that one's 3, that one's 4, and that one's 5. And that will help orient you as we go ahead and fill out the products here. So in short, what we can do with alkynes right now is we can do reductions. We can reduce those down. We can add hydrogen across the double or triple bond and get down to products that are saturated as opposed to these unsaturated products. So here I've drawn a 5-carbon group, and so hydrogen gas and palladium on carbon, what it does is deliver 2 molecules of hydrogen gas across the triple bond, and they end up occupying those spots. And what it does is add one first and then the other one second. And so carbon 1, carbon 2, carbon 3, 4, 5, that's how you orient relative to where we were. And so what happens first is you take a molecule of hydrogen gas and you put 1H on the 2 position, 1H on the 3 position, which eventually leads to a alkene, which then you do the same exact thing again. And so your final product when you use hydrogen gas and palladium on carbon is that. You could also abbreviate the hydrogen gas as I have drawn it up there, the way I've drawn it right here, which is just H2. So H2, of course, being the same thing as hydrogen gas. So alternatively, what we could do is take hydrogen gas and Lindlar's catalyst, which is basically palladium, but poisoned so it can't react as quickly as before, and you poison it with a little bit of barium sulfate. And what that does is allow you to trap the intermediate product along the way. So in other words, rather than passing through the cis alkene and continuing on to the saturated system, you stop here. So what Lindlar's does is it stops the reaction halfway, and specifically it stops it at the cis alkene. And again, position 1, 2, 3, 4, 5. All right, so the key feature of this is that this is a slower reaction, which allows you to trap things out. But actually, the palladium on carbon by itself reacts preferentially with alkenes in the presence of alkynes, so you can never isolate the cis material using palladium on carbon. Add in the barium sulfate though, and it stops here. And of course, it's not going to be super valuable to generate only the cis material if you can't also generate the trans material. And so that's why we have these set of conditions right here, which is sodium metal, so sodium 0, sodium metal, not sodium plus, sodium metal, and ammonia liquid as a solvent. So sodium 0 and ammonia liquid, that's how you make the trans material. Carbon 1, carbon 2, 3, 4, 5. Now, I'm not going to ask you to generate these mechanisms on a quiz or exam or anything like that, but it is valuable to walk through why this works the way it does so you can see what's going on. So really what you want to think of is having palladium metal as this sort of surface that's just sitting there, so metal flat surface. And then what you have is a hydrogen gas molecule come floating by, and it's going to orient itself kind of like this. But palladium metal, palladium 0, has a pair of electrons on it, and that pair of electrons then can get involved in this mechanism. And what can happen is those electrons can come and make a bond to that hydrogen, while this pair of electrons that was between the 2 hydrogens now makes a bond to the palladium surface. And so what you do is you end up swapping around the electrons and creating a scenario where the palladium surface now has 2 H's bound to it. And then if a double bond or a triple bond were to come floating nearby this palladium surface with the hydrogens on it, then what can happen is you can deliver an H- to one end of the double bond, while the double bond then pops off to abstract an H+ from the other side, and that causes a pair of electrons to end up back on the palladium surface. And so it is this sequence all happening at the same time, all from the same side, is what governs the process and why you get the cis material. You deliver both H's simultaneously from the same side of the triple bond, which is why you can isolate the cis double bond material. So the mechanism, the reason why this happens is this all happens at the same time. This is what we would call a syn addition from the same side, and it all happens simultaneously. So the key features of the mechanism to deliver the cis product are that you come from the same side at the same time, as opposed to, of course, the mechanism that happens down here. And the main reason why I'd want to show you the mechanism for the sodium metal is because it's our first opportunity to deal with single electron processes. So sodium has 1 electron on it, sodium metal does, because it wants to become sodium plus. And so this is going to be a very bizarre looking mechanism, but what happens is this single electron goes and causes this triple bond to break. So this particular bond would, say, break this way, and what that'll lead to in the immediate short term is a very bizarre and very high energy intermediate. That should make you shudder a little bit to look at, because what we've done now is put a lone pair on a carbon, put a minus on a carbon, which should make you cringe a little bit. And at the same time, we've added an extra electron to the other side. So we've really only added one electron, but we caused these things to split in such a way that you have a single unpaired electron on that carbon, which should make you feel bad. And you've got a minus charge on that one, which again, sure doesn't look right either. And that combination just really shouldn't happen at all. So why does it happen? Well, the driving force for the entire process is the fact that sodium really doesn't want to have a single electron. And so what it's trying to do is get rid of that single electron, and this is just a nearby place that can do it. And so it's the energy of getting rid of that single electron on sodium, making sodium plus, that is really what drives this. So you've got the minus charge generated there. Of course, we've got a sodium plus floating around nearby. And now you know that this is a really unpleasant scenario for that carbon, not even taking into account the radical nearby. This is a pK of about 45. So if you have ammonia, which is a pK of about 35, that's 10 to the 10th downhill, and that will end up forming the sodium amide. This initial step, by the way, was a one-way step, and then this deprotonation, likewise, is going to be a one-way step. This is not coming back from that. And so that leads to this radical in the intermediate stage. Now, what happened next, of course, is that you've got another sodium metal nearby that has a single electron on it. That will end up donating one electron to become a lone pair, and then you pull off another hydrogen, and that leads to your final material there. Again, do I want you to be able to generate this mechanism? No. But the reason why I'm providing it for you is that it really shows why you end up with the trans stuff. Right here, this horribly electron-heavy, electron-rich molecule is going to want to orient in such a way to get those electrons as far apart as possible. So it's the fact that you have a minus at the same time as you have a radical. Now, orient those as far apart as you can, forces it to be trans. And then once it's trans, well, it stays trans, and that's your final product right there. So these happen all from the same side and at the same time. This happens sequentially and also in such a way as to want to rotate around and get those minuses as far apart as possible.